In this lesson, we're going to take a look at the relationship between derivatives and the concept of continuity that we introduced when we were studying limits. We'll begin by introducing something called local linearity, which is relevant to this discussion, and then we'll look more closely at that relationship between differentiability and continuity. Let's look at local linearity to start. To do this, we need to establish a bit of vocabulary involving differentiability at a point. So recall that when we're finding the derivative of a function, the process we are carrying out is called differentiating the function. And the root here is the word difference in the sense of subtraction. Recall that we find a function's derivative by taking a limit of what's called a difference quotient. So if we have a function f, let's say that we can find f prime of a for some value of a, f prime of 2 or something like that. In that case, we say that the function f is differentiable at a. In other words, we are able to find the value of its derivative at that input value. To see an example of a function that is not differentiable at a point, there are a few clues we can look for. We'll take a look at a straightforward example to begin with. The most straightforward examples of this kind of thing are those where the derivative expression is undefined for a given x value that we're interested in. So let's use an example of a function whose derivative we've already found. Let's say that f of x is equal to 1 over x squared. Well, we saw earlier that the derivative f prime of x for this function is negative 2 over x cubed. We were able to find that by using one of our definitions of a derivative. Now, if you look at that derivative function, negative 2 over x cubed, that's undefined at 0. So in other words, f prime of 0 is undefined. Another way of saying that is that f is not differentiable at 0. In other words, we cannot find a number that represents the derivative of our function at 0 because the derivative function in this case is undefined. To see why this kind of thing can happen, why a function can fail to be differentiable at a point, let's look at this idea of local linearity. So recall how we came up with the idea of a derivative. When we find a derivative or when we differentiate a function, we use secant lines of the graph of the function to give us better and better approximations of the behavior of a function at a particular point. And as long as very close to the point we're interested in, the graph of the function looks a lot like a straight line, this works great. When this happens, we say that our function is locally linear near that point. In other words, near that point in that location, the function is basically like a straight line. So just to give you an example, here is a graph we've used before to illustrate a function's graph and the tangent line of the graph at a particular point a, f of a. And if we zoom in very close to that point a, f of a, you can see that the tangent line in red and the graph of the function in blue look very, very similar. And if we were to keep zooming in, they would look more and more similar. Eventually, we would get so close to that point that you wouldn't be able to tell the tangent line and the graph of the function apart. The graph of the function would look just like a straight line. That's what we mean when we say that a graph or a function is locally linear near a point. There's a connection between local linearity and differentiability. The rule of thumb here is that a function will be differentiable at a as long as it's locally linear near a. In other words, as long as its graph and the tangent line of the function there look pretty much the same. There is one exception to this. It involves vertical lines where the graph can be locally linear but still fail to have a derivative. We'll look at that in a little bit. But what this allows us to do is to establish some criteria for when a function has a derivative at a point. And there's a few different things we could say here. We'll concentrate on the relationship between differentiability and continuity, which is where the details of this are most significant. So let's first see why differentiability requires continuity. To see why this is, let's consider what happens when a function is discontinuous somewhere and how that affects its local linearity. Basically, when a function is discontinuous, that breaks its local linearity. Straight lines are always continuous, which means that if you have a discontinuous function or a function that's discontinuous at a particular place, then if you zoom way in on that discontinuity, no matter how close you get, as long as you can see that the function is discontinuous, there's no way it'll look like a straight line because straight lines are continuous. So here's an example. Let's take a look at the graph of y equals x squared minus 1 over x minus 1. We'll look around the point where x equals 1, and there's the graph. And there's a point discontinuity or a hole in the graph at that point where x equals 1. And no matter how close you get to that point, that hole is always going to be there. There's no way that you can get close enough to the graph around that point to make that hole disappear. It's always going to appear there. You'll always notice it. And so you will never, in effect, confuse this graph for a perfectly straight line with no holes or breaks or discontinuities in it whatsoever. So in other words, our graph will always be clearly distinguishable from a line, which means that it is not locally linear near where x equals 1. And so what this shows us is that continuity is a requirement for differentiability. The same thing we saw with that point discontinuity applies whenever you have a discontinuity, whether it's a point discontinuity, a jump discontinuity, a vertical asymptote, whatever it might be. Any of these things break the function's local linearity. And so that allows us to set down a requirement for a function to be differentiable at a point. The function we're talking about, let's call it f, is differentiable at a only if f is continuous at a. Or in other words, the function has to be continuous in order to be differentiable at a. Another way to put the same thing, if a function is discontinuous at a, it is not differentiable at a. So if you know that a function is discontinuous at a particular point, you know right away that it is not differentiable there. The shorthand slogan version of this is that differentiability requires continuity. On the other hand, continuity does not require differentiability. Let's see why. The key here is that we can have continuity without local linearity. So what we're looking for here are examples of continuous functions that are not locally linear near certain points. And if we can find one such function, that shows us that a function can be continuous at a point, but fail to be differentiable there. One function that illustrates this quite clearly is the absolute value function. Let's take a look at it. We're going to look at the graph of that y equals the absolute value of x very close to the point where x equals 0. There we go. You can see from the scale markings on each axis that we're zoomed way in on where x equals 0. So we're only looking at points very, very close to where x equals 0. And no matter how close we get, even if we were to zoom in a whole bunch more, that very sharp turn you see in the graph will always be there. There's no way to get close enough to the point where x equals 0 on this graph to make that go away. And of course, because that sharp turn is there, this graph does not look like a straight line. Straight lines never have those kinds of sharp turns. So we can never get close enough to where x equals 0 here to make this graph look like a straight line. Therefore, our function is not differentiable at x equals 0 because it's not locally linear there. But you can see from the graph that the function is continuous there. There's none of the kinds of behavior that would lead to discontinuity. There's no hole, no jump, no asymptote. We have a continuous function. Another more analytical way to see this is to consider the idea of a one-sided derivative. So a one-sided derivative is what we get if we take our usual derivative definition. Either one will work. We'll use the first definition we introduced, but we consider the one-sided limits as, in this case, h approaches 0 rather than the ordinary limit. So we can talk about the derivative of a function from the left by taking the limit as h approaches 0 from the left, and then we have our usual difference quotient that we're applying the limit to. Or we could also have a derivative from the right where we take the limit as h approaches 0 from the right. So the way to think about these is in terms of where the second point that defines our secant line is relative to the point we're keeping fixed. In the case of the first derivative, the derivative from the left, we require that the other point on our secant line be to the left of the point that we're moving it closer to. Whereas in the derivative from the right, we require that the derivative or the second point in the secant line be to the right of the point we're keeping fixed. And we can use one-sided derivatives to consider differentiability a little more closely. Derivatives are limits of a sort. And so like any limit, in order for the ordinary limit to be defined, the corresponding one-sided limits have to be defined and they have to agree with each other. This means that a function will be differentiable at a point only if its one-sided derivatives there agree with each other. And as long as our function is locally linear, that will happen. If your function is locally linear at A, then the one-sided derivatives will agree, the function will be differentiable at A. But for things like we saw earlier, the absolute value function at x equals 0, the one-sided derivatives disagree with each other, which is why one of the reasons why differentiability breaks down here. Let's see why that disagreement happens. So one way to see what's going on here is to use a piecewise definition of the absolute value of x. There it is. So we can say that the absolute value of x equals negative x if x is less than 0, and positive x if x is greater than or equal to 0. So that negative x in the first row basically accounts for the fact that if x is less than 0, it's already negative. So taking its opposite will make it positive. Now, if x is to the left of 0, then the absolute value of x is just like negative x. That's what our piecewise definition tells us. And the derivative of negative x is the constant -1 function. In other words, the derivative of the absolute value of x from the left is -1. In other words, any tangent line that we draw on the graph of the absolute value function to the left of where x equals 0 will have a slope of -1. But to the right of where x equals 0, our graph of the absolute value function behaves just like the ordinary y equals x graph, whose slope is +1, which means that the derivative from the right is +1. So notice that our one-sided derivatives disagree with each other. The derivative from the left is -1, the derivative from the right is +1. Since those disagree, the ordinary derivative is not defined and the absolute value of x is not differentiable at x equals 0. Let's look a little more closely at the graph of the absolute value function near where x equals 0. The reason to do this is because often you can see from the graph that what we just observed happens, and you don't need to consider the one-sided derivatives in detail. You'll be able to see from the graph what's going on. So let's look at the graph of y equals the absolute value of x near where x equals 0. Again, there's the graph. And notice that that point at x equals 0, where the graph turns around, so to speak, is a sharp turn. It happens all at once. It's not smooth and gradual like you see in a parabola at its vertex. The turn happens kind of instantaneously. We call these kinds of things corners of graphs, these kinds of very sharp, instantaneous turns. And when you see one of these in a graph, if you see that a graph has a corner at a particular point, you know right away that the function is not differentiable there. Because although you don't always need to go through the work to figure this out, the one-sided derivatives will disagree. The corner is the graphical giveaway that happens. There are also slightly different sorts of shapes that work kind of the same way. They're called cusps. So here's another example of a function that is not differentiable because it has one of these kinds of sharp turns. It's the graph of y equals the cube root of x squared. There's the graph of this function. And notice that at x equals 0, again, we have a kind of sharp turn. So just like we saw with the absolute value function, this function is not differentiable at x equals 0. And again, you could zoom way in on that if you want. No matter how close you get, you will never make this look like a straight line near where x equals 0. Now, in this case, the graph is a little bit different from the absolute value graph because the graph is sort of bending inward as we get closer to where x equals 0. We call that kind of behavior in a graph a cusp. But in practice, they work just like corners. Finally, there are cases where a graph has a vertical tangent line at a point. So this is a third way, besides cusps and corners, where a graph can be continuous at a point without being differentiable there. An example of a function that has this behavior is the cube root function at the point where x equals 0. So here's the graph of the cube root function. And at the instant or right at the point where x equals 0, the graph is sort of pointing straight up. The tangent line there, in other words, is vertical. And since it's a vertical line, it has no numerical slope, which means that the derivative, which would give us the slope of the tangent line, is undefined. Undefined tangent line slope means an undefined derivative. And so this is another case in which the function is not differentiable at a particular point where x equals 0. In this case, it's because the slope of the tangent line is undefined, even though there is a tangent line there. There are some clues, analytical clues, that you can have a vertical tangent line. They're usually pretty easy to find analytically, so you don't have to rely on having a graph of your function. The way to tell you have a vertical tangent line of a function f where x equals a is, first of all, if the function is continuous at a, and second, if you try to find f prime of a, you end up dividing by 0. So our example from a moment ago, the cube root function was a function that is continuous everywhere. So it's continuous where x equals 0. Its derivative, though, we don't have the tools to find this yet, but we will soon. Just take my word for it right now, that the derivative of the cube root of x is 1 over x to the power 2/3. Like I said, we'll have a formula soon that will allow us to find that derivative quite quickly. But for right now, just notice that if x is equal to 0, that derivative function has 0 in its denominator. That tells us that the cube root function has a vertical tangent line at x equals 0.